Hello everyone, myself Hans. Today we are going to solve the problem of complex integration based on the calculus of residue theorem. Here in the question, using complex variable, evaluate the real integral 0 to 2 pi d theta upon 1 minus 2p sin theta plus p square where p square is less than 1. Let's solve the problem. Given integral is 0 to 2 pi and d theta upon 1 minus of 2 p sin theta plus of p square. And further we have to know in the complex integration z is equal to e to the power I theta, and from here differentiating with respect to theta, that is dz is equal to e की power I theta, and again I की power I theta differentiating with respect to theta, that is I into d theta, and again put the value of e की power I theta, that is z, that is dz is equal to Iz d theta. Further we have to find the value of d theta, that is d theta is equal to dz upon Iz, and we also know in the complex integration sin theta is given by 1 upon 2i and z minus 1 upon z. Further we have to put the value in the given integral, that is I is equal to, taking close integration. Here C represent unit circle and unit circle is given by mod z is equal to 1, and poles are given lengths which are lies inside the given circle, that is we have to put 1 upon 1 minus 2p, and the value of sin theta is given by 1 upon 2i and z minus of 1 by z and plus of p square, and the value of d theta is given by dz upon Iz. Further we have to take LCM in the denominator, that is I is equal to, we can also cancel the term, 2 से 2 cancel out, then remaining is c 1 upon, taking LCM here, that is here is once again 1 minus of p upon I, and here is taking LCM z square minus of 1 upon z plus of p square and dz upon Iz. Further we have to solve, that is close integral 1 upon, we have to take LCM Iz with this, that is Iz multiplied with 1, that is Iz, and from here that is minus of pz square and plus of p square, and here is p square multiplying with Iz, that is once again plus of p square Iz, and here is dz upon Iz, and upon here is zi Iz. Further we have to cancel the terms, Iz to Iz is cancel out, then the remaining is close integral 1 upon here is Iz, we can also write it is zi, and minus of pz square, we can also write in place of I square in complex integration, that is I square is given by minus of 1, so we have to put here plus of I square pz square and plus of p square, and here is plus of p square Iz, and here is dz. Further we have to take a common from denominator, that is close integral 1 upon, here we have to take a, once again we have to take From here that is zi is taking common, that is zi is taking common, then remaining is 1 plus of, here is z as I z, here is I z p, and from here we have to take common p square, that is, once again, here is not p square multiplying with p with minus 1, that is, this is p and this is also p, so we have to take common from here plus of p, and this is 1 plus izp upon dz. Further we have to write, that is close integral c and dz upon, here is zi plus of p and 1 plus of izp. Further we have to find the simple poles. Find simple poles taking denominator is equal to 0, we have to take our denominator is equal to 0 to find the simple poles, that is zi plus of p is equal to 0 and second bracket, that is 1 plus of izp is equal to 0. From here that is p is equal to minus of zi, and from here we have to find the value of z, and from here that is izp is equal to minus of 1, and from here we can also write, that is, once again, this is zi is equal to p, that is, we have to find the value of p, that is, we can also write, that is z is equal to minus of p upon I, and we know that in the complex integration I square is written as minus of 1, so we have to put in place of minus 1 minus, that is I square, that is I square p upon I. From here I to I is cancelled out, then the remaining is pi, and further in the second bracket we have to solve, that is, we can also write, that is z is equal to minus of 1 upon zi, and from here we can also write the, from here in place of minus 1 we can put, that is I square, that is I square upon zi, and I to I is cancelled out, then the remaining is I upon z, and here in the C represent the unit circle, and unit circle the poles lies inside the given circle at z is equal to pi, so we have to further find the residue at z is equal to pi. Find residue at z is equal to pi. From, we can also, once again, we can also write the given terms in the form of, once again, that is I is equal to close integral c and dz upon, we have to take common from I here, that is I is taking common, that is, once again, z plus of pi, z plus of p upon I, and 1 plus of, once again, we have to take common from 1 plus of izp, we have to take common I, that is I is taking common, that is zp plus 1 upon I, and once again we have to put, no, so we have to common from here, that is I is taking common, that is z plus of p upon I, and the second bracket is 1 plus of izp, and we have to take common from, we can also write, that is 1 upon I and close integral C, and here is we have to let fz dz. So fz dz, we have to find the poles at fz dz, z is equal to pi, and we have to find residue at z is equal to pi, that is limit z tends to pi, and here is we can also write that is z minus of pi, that is z minus of pi, and here is remaining is 1 upon, this is, once again, here is z plus of p upon I, and the second bracket is 1 plus of I z p. Further we have to put in place of z is equal to pi, these terms is eliminated, and we can also put here in place of z is equal to pi, that is pi, and again taking LCM, that is pi square, and the value of I square is minus 1, so we have to minus p plus p, this bracket is also cancelled out, and the remaining is 1 upon 1 plus of izp, so we have to put here, that is 1 plus of I, and in place of z we have to put pi, and again remaining is also pi, so we have to multiply these terms, that is 1 upon 1 plus of I into I is I square, and I square is given by minus of 1, so we have to put here minus, and p into p is p square. Further we have to put the, we know the, once again, and here is 1 upon I is present, so we have to write Cauchy residue theorem, Cauchy residue theorem, close integral fz dz is equal to 2 pi I into sum of residue, here r plus present, sum of residue, we have to find the sum of residue, that is 1 upon 1 minus of p square, and here is fz is given by, that is 1 upon I is remaining, and here is into 2 pi I, and sum of residue we have to find, that is 1 upon of 1 minus of p square, and from here that is I to I is cancelled out, and the remaining is 2 pi I upon 1 minus of p square, and we can also write the terms I is equal to, that is close integral 0 to 2 pi and d theta upon 1 minus of 2p sin theta plus of p square is equal to 2 pi upon 1 minus of p square. This is the required solution of the given problem. Thank you class, and thank you for watching.